tension, capillarity. These points are there, and some parts are there in fluid statics. So let's start with fundamental concepts. So let's start with fluid definition. So fluid is a substance that deforms continuously under the application of shear stress, no matter how small the shear stress is. So in other words, we can say that any substance which is capable of flowing, that is nothing but fluid. So if I apply small tangential force to the fluid, it will continuously deform. Like in case of solids, if we apply a small force, tangential force to the solids, then it will not deform, or it will deform up to some extent, and that resistance is also high. But in case of fluids, the resistance is very small. We can compare the solids and fluids by using these points. So in case of solids, it is more compact molecular structure, and in case of fluids, it is less compact molecular structure. Remember, in case of fluids, liquids are there as well as gases are also there. Then in solids, it can resist tangential force, that is that we can find out by using the shear stress. And in case of fluids, the negligible resistance is there, but that resistance is very small. Then in case of solids, deformation is constant with respect to time. But in case of fluid, rate of deformation is constant with respect to time. Okay. And solids have some definite shape. Fluid does not have any definite shape. When we remove the force from the solid, it will regain its original shape. In case of fluids, it will not regain its original shape. Right? Then there are certain assumptions. Mainly two important assumptions are there in fluid mechanics. First is fluid as continuum. So we are always assuming that our fluid is continuous. That means there is no void space, and that can be governed by using Knudsen number. So by using Knudsen number, we can identify whether the fluid is continuum or not. So this Knudsen number is non-dimensional number. So it is the ratio of mean free path to the characteristic length. If Knudsen number is less than 0.01, then we can say that fluid can be considered as continuum. Otherwise, fluid is not continuum. Now, whatever the laws, whatever the things we are learning in this fluid mechanics course, these all things are applicable when the fluid is continuum. When the fluid is not continuum, some of these laws are not applicable. Second assumption is no slip condition. That states that the first layer, whenever fluid it is in contact with the solid, the first layer will directly attach with that solid surface, and it will have same velocity as that of the solid surface. Okay, this is the second assumption. So these two assumptions are there in fluid mechanics. Then let's start with the properties of the fluids. So you can see there is one cylinder, and inside that cylinder, some 5 types of fluids are there. So we can easily understand that because of density, the fluids are separated. So first concept is density, that is also known as mass density or specific mass. It is the ratio of mass per unit volume. Unit is kg per meter cube. Second concept is specific weight, or that is also known as weight density. That is nothing but weight per unit volume. So its unit is Newton per meter cube. Likewise, third concept is specific volume. It is reciprocal of density. Unit is meter cube per kg. And fourth concept is specific gravity. That is density of any fluid to the density of water, and it is dimensionless property. See, these concepts are very much important because many times we want to find out the weight of the fluid element or mass of the fluid element. So always in case of fluid mechanics, we are writing mass in terms of density into volume, because density for a substance is fixed. So by using the volume, we can find out the mass. Likewise, weight we are calculating as weight density into volume. So that's why these concepts are very much important. By using the specific gravity also, we can find out the density. So let's solve one simple numerical based on this. So in this numerical, you have to find out the specific weight, mass density, specific gravity, and specific volume of oil having volume of 4.5 meter cube, and its weight is 40 kilonewton. Okay, always use SI units. So volume is given as 4.5 meter cube, and weight of the oil is 40 kilonewton. So if I convert that into Newton, it is 40 into 10 raised to 3. Now we want to find out specific weight. Specific weight is nothing but weight density. Mass density, that is simply density. Specific gravity, that is S or relative density we can say, and specific volume, that is reciprocal of density. So we can just put the values and we can find out these values. So specific weight is weight upon volume. We'll put that values and we are getting the answer. Remember, always write the units. Units are important. Then mass density, you can see it is almost 906.1 kg per meter cube. Specific gravity, that is 0.906. And specific volume is 1.1 into 10 raised to minus 3 meter cube per kg. Now, fifth property is viscosity, that is also known as dynamic viscosity. In simple words, we can say that resistance to the flow, that is nothing but viscosity. This viscosity is majorly because of cohesion and molecular momentum exchange. Because of these two things, the viscosity is there inside the fluid, or we can say that viscosity is nothing but frictional loss inside the fluid. Then what is the effect of temperature on the viscosity? Now, it depends on whether it is a liquid or whether it is a gas. Now, in case of liquids, cohesion is predominant. So, as temperature increases, cohesion decreases and molecular momentum exchange increases. But in case of liquids, cohesion is predominant. So, whatever the effect is there on the cohesion, same effect will be there on the viscosity in case of liquids. Remember, this is in case of liquids. So, as temperature increases, in case of liquids, cohesion decreases and molecular momentum exchange increases. That's why viscosity decreases. Now, in case of gases, as temperature increases, again the thing is same. That is, cohesion decreases and molecular momentum exchange increases. But in case of gases, this molecular momentum exchange is predominant. So whatever the effect is there on molecular momentum exchange in case of gases, same effect will be there on the viscosity in case of gases as we increase the temperature. Okay. So in case of gases, as we increase the temperature, viscosity increases. We can see this graph. So in case of liquids, as we are increasing the temperature, viscosity goes on decreasing. And in case of gases, as we are increasing the temperature, viscosity goes on increasing. Then there is one important law, that is Newton's law of viscosity, that states that shear stress is directly proportional to the rate of shear strain, or we can say that velocity gradient, because rate of shear strain, that is equal to the velocity gradient. Mathematically, we can write like this: shear stress, that is equal to mu du by dy. The terms are shear stress, that is nothing but tangential force upon area, or we can say that it is viscous force upon area. Mu, that is nothing but viscosity of the fluid, that is the property of the fluid. And du by dy, that is rate of shear strain or shear rate or strain rate or velocity gradient. Okay. Then by using that also we can define the viscosity. So viscosity, we can say that it is the ratio of shear stress to the velocity gradient. Now different units of viscosities are there. So SI unit is Pascal second. You can find out that. You can you can put the unit of viscosity, shear stress and velocity gradient. You will get SI unit of viscosity is Pascal second, or that is also equal to Newton second per meter square. CGS unit of viscosity is dyne second per centimeter square, and that is also known as poise. Remember one thing, 1 Pascal second, that is equal to 10 poise. So many times in the numerical, the values of viscosities are given in the poise, and we want SI units. So we have to convert that poise into Pascal second. Then based on the viscosity, we can differentiate the fluids. So majorly, broadly, we can differentiate like ideal fluid and real fluid. Ideal fluid does not have any viscosity. So viscosity is 0 in case of ideal fluid. Real fluid has viscosity. In case of real fluid also, we can uh, subdivide the fluids like Newtonian fluid and non-Newtonian fluid. Newtonian fluid means the fluid which obeys Newton's law of viscosity, that is known as Newtonian fluid. And the fluid which does not obey the Newton's law of viscosity, that is non-Newtonian fluid. Now in case of non-Newtonian fluid, there are several types like pseudoplastic fluid is there, dilatant fluid is there, Bingham plastic fluid is there, rheopectic fluid is there, and thixotrophic fluid is there. These all types of fluids we can define by using this mathematical equation, that is shear stress, that is equal to A plus B du by dy raised to n, where this A, B and n are constants. This A, B and n depends on which type of fluid it is. So by using this graph, you can understand for the Newtonian fluid, the shear stress, shear stress is directly proportional to the deformation rate or velocity gradient, that is du by d bar. That is for Newtonian gradient, Newtonian fluid. And the slope of this curve indicates the viscosity. Okay, so for the Newtonian fluid, viscosity is always constant. For pseudoplastic fluid, you can see the viscosity is changing. Likewise, for the dilatant fluid also, the viscosity is changing. Okay, we can see the different examples of pseudoplastic fluid and dilatant fluid. Like for the pseudoplastic fluid, it is a blood. For dilatant fluid, example is butter. Likewise, for Bingham plastic fluid, it is a toothpaste. Now, in case of Bingham plastic fluid, we need some initial stress. We need some initial stress value like this. And after that, if we apply the stress, it will deform continuously, just like a Newtonian fluid. Likewise, thixotropic fluid is also there, rheopectic fluid is also there. Then we'll try to solve some numericals based on this dynamic viscosity. We'll solve only some sample numerical here. So this is the question. A dynamic viscosity of oil used for the lubrication between the shaft and sleeve is 6 poise. So dynamic viscosity is given, but that is given in terms of poise. You have to convert that into Newton second per meter square. Shaft diameter is given, that is 0.4 meter, and it rotates at 190 rpm. So its rotational speed is given. Then you have to find out power lost in the bearing for the sleeve length of 90 mm. Thickness of oil film is given, that is 1.5 mm. So this diagram is provided. Shows shaft diameter is 0.4, sleeve length is 90 mm, and thickness is 1.5 mm. So these things are given. Just I have converted that into SI units. Now we are using Newton's law of viscosity. Whatever the numericals are there based on the viscosity, all the numericals are able to solve by using the Newton's law of viscosity only. So this is Newton's law of viscosity. In that, this du is change in velocity and dy is change in distance. So we can find out the u since only the shaft is rotating and sleeve is not rotating. So there is only one velocity, and that is rotational velocity. We have to convert that into linear velocity. That we can do by using this formula, that is u is equal to pi dn by 60. So just I'm putting the values, I'm getting the u as 3.98. Since the sleeve is not rotating at all, so this is my change in velocity only, that is 3.98. And the thickness is given, that is 1.5 into 10 raised to minus 3. So I'll put these values in this equation. So by using that, I will able to find out shear stress. So in my case, shear stress is 1592 Newton per meter square. So you can see this is the value of shear stress. Actually, we want to find out power lost. So power loss we can find out by using this formula, 2 pi nt divided by 60. So we want actually torque. We have got the shear stress, but we want torque. So first we will find out the force. So force we can find out as shear stress into area, surface area. So by using that, we are getting the shear force. That is also known as viscous force. So by using this force, we are able to find out the torque. That is torque is force into radius, that is diameter divided by 2. So the torque is 36.01 Newton meter. So well, after putting the values, I'm getting power lost as 616.48 watt. Then similar kind of numericals I already solved in my different videos. Please subscribe to the channel and please go through these videos. Apart from this, you may find the numericals like one horizontal inclined plate is there, and on which one plate is there. And in between these two plates, one fluid is there. And the question may be like, we have to find out the how much velocity is there for this plate, or how much force is required. That kind of numericals, please try to solve. Apart from that, the numericals are given in this video, some simple numericals, okay, and some medium to hard numericals are given in this video. Then let move to the next property, that is sixth property, kinematic viscosity. It is the ratio of dynamic viscosity to the density. So we can find out the unit. So SI unit is meter square per second. CGS unit is centimeter square per second. That is also known as Stokes. And 1 meter square per second is 10 raised to 4 Stokes. Then next property is compressibility and bulk modulus. So let's define the bulk modulus. It is the ratio of compressive stress to the volumetric strain. Or in other words, we can say that volumetric stress to the volumetric strain. That is also nothing but bulk modulus. Or we can say that it is increase in pressure to the volumetric strain. So mathematically that we can write as K is equal to dP divided by dV by V. Okay, so dV is change in volume and V is original volume. The negative sign indicate that when we are increasing the pressure, the volume goes on decreasing. That's why the negative sign is there in this bulk modulus. And compressibility is reciprocal of bulk modulus. That means for a substance, if bulk modulus is very high, that means that fluid, that substance is not easily compressible. Okay, so we can say that we can see that for liquids like water, the bulk modulus is 2 into 10 raised to 6. You can see this amount is very high. And for the gases like bulk modulus of air, the value is 101 kilonewton per meter square. So we can compare these two values. So we can see that bulk modulus of liquids are very high as compared to the bulk modulus of gases. Okay. So in other words, we can say that the liquids are nearly incompressible while gases are compressible. So bottom line is for any fluid, if bulk modulus is high, that means that is not easily compressible. Next concept is vapor pressure and cavitation. So vapor pressure measures the tendency of any substance to change into gaseous or vapor state with increase in temperature. That is indicated by vapor pressure. So we can see vapor pressure of water at 20 degrees centigrade is 2.33 kilonewton per meter square, while vapor pressure of petrol at 20 degrees centigrade is 30.5 kilonewton per meter square. And we know that petrol vaporizes faster than the water. Okay, so the fluid which has a vapor pressure high at a particular temperature, that indicates that fluid will easily vaporize. Then this is the vapor pressure of water at different temperatures. So in other words, we can say that these are boiling point temperatures and pressure for the water. That means at 100 degrees centigrade, at 1 atmospheric pressure, the water will boil. Okay. If it goes on reducing the temperature, the pressure also need to reduce. Then and then water will boil. Likewise, if we increase the pressure, the boiling point temperature of water will increase. Next is cavitation. Cavitation is formation of vapor bubbles in a low pressure region, and with the direction of the flow, that bubble is moving, and when it collapses in the high pressure region, the pitting action will happen. That is cavitation. So you can see this impeller. You can see this on this impeller, this pitting actions are happen. This is because of the cavitation. Then last property, surface tension and capillarity. So surface tension is phenomena in which surface of the liquid behaves like it is always in a tension, just like an elastic sheet. So we all know that different examples of surface tension, like insects can walk on the water surface, that is because of the surface tension. Droplets are formed because of the surface tension also. On a coin, we can put some liquid and it will not fall up to some region. That is because of the surface tension also. Then we can find out surface tension in different cases, like for the drop, or in other words, we can find out how much pressure is there in a drop. That drop may be water drop, that may be oil drop. Okay, so that we can find out by just balancing the forces, whatever the internal pressure force and whatever the outer surface tension. These two forces we can balance. So by balancing that, we'll get that for a drop, pressure inside the drop is 4 sigma divided by d. The sigma indicates surface tension. Likewise, for the bubble also we can reduce. Only important steps are given. For detailed description, please refer some books. Now, in case of bubbles, there are two surfaces, one outer surface and one inner surface. So that's why two times surface tension is there. So by using that also we can find out the pressure inside the bubble, and that is 8 sigma by d. Likewise, we can find out pressure inside a liquid jet, and that is 2 sigma by d. Then capillarity, it is a rise and fall of liquid in a narrow space, or we can say that it is a thin tube, in a thin tube. Like in this first image, the liquid is rise inside the tube, and in the second image, the liquid is fall. Capillary action will happen if the diameter of the tube is less than 6 mm. Then how much height is raised or how much height is fall, that we can find out just by balancing weight of that liquid column, and that is equal to the surface vertical component of surface tension force. By balancing these two forces, we can find out what is the height of that liquid column. So ultimately we are getting this formula. So this height h, whatever this height h, or we can say this height h, this we can find out by using the same formula, that is 4 sigma by rho gd. Okay, so by using this we can find out the capillarity, rise or fall. Different examples are there, real life examples, earthen pot, then photosynthesis process, or how the liquids are going from the root to the leaves. So that we can explain with the help of this capillarity. So likewise, different examples are there. Okay, then we will move to the second part, that is fluid statics. In fluid statics, these are the important points, like pressure is there, Pascal's law is there, hydrostatic law is there, then manometers are there, then hydrostatic force and center of pressure in different cases. The Archimedes principle, buoyancy and stability criteria in floating bodies and submerged bodies. So let's start one by one. Pressure is a normal force, or we can say that perpendicular force per unit area. That is nothing but pressure. So mathematically we can write pressure is force upon area. Unit is Newton per meter square or Pascal. This is the unit. Apart from that, different units are there. Pressure we can measure in atmosphere also. So 1 atm, that is also one of the unit of pressure. We can measure the pressure in terms of liquid column, that is in terms of mm of Hg or meter of water or meter of any liquid column. We can measure the pressure. Then torr is also one of the unit of pressure. 1 torr, it is equal to 1 mm of Hg. Pascal, that is Newton per meter square, that is also one of the unit of pressure. Pascal, kilopascal, megapascal, gigapascal. Then bar, millibar, and psi, that is pounds per square inch. That is also one of the unit of pressure. Then 1 atmospheric pressure we can write in different units. Like in ATM, it is 1 atmospheric pressure. In terms of mercury column, it is 760 mm of Hg. In terms of torr, it is 760 torr. In terms of Pascal, it is 101,326 Pascal. In terms of kilopascal, it is 101.325 kilopascal. In terms of bar, it is approximately 1 bar, likewise. Then there are two scales of pressure. One is absolute pressure and one is gauge pressure. So the relationship between these two is absolute pressure, that is equal to atmospheric pressure plus or minus gauge pressure. So gauge pressure we are measuring with respect to local atmospheric pressure, and absolute pressure we are measuring with respect to absolute zero pressure. Okay, so accordingly positive gauge pressure is there, negative gauge pressure, that is also known as vacuum pressure, suction pressure, or negative gauge pressure. That is the pressure below the atmospheric pressure, that is negative gauge pressure. So we can find out absolute pressure by using this relation. Then Pascal's law states that the pressure or intensity of pressure at a point in a static fluid is equal in all direction. In different books, they are writing this Pascal law in different words, but the meaning is same. That is, pressure at a point in a static fluid is equal in all direction. So mathematically, we can write that is Px that is equal to Py into Pz at a point in a static fluid. Second law is hydrostatic law. That tells us that rate of increase of pressure in vertical and downward direction is equal to the specific weight of the fluid at that point. Mathematically, we can write like this. So dou P by dou Z. Z indicates direction in vertically downward direction. So dou P by dou Z, we can say that it is rho G, that is specific weight. Or we can reduce this equation if density is constant, then pressure is rho GH or rho GZ. So we can find out pressure at any location. So in this image, we can see pressure at bottom is rho GH. Pressure at bottom is rho GH. So likewise, we can find out pressure at any point. Just we need the height from the free surface. Like if you want to find out pressure at this point, then we need the height from the free surface, this height. So by using this, we can find out pressure at this point, that is rho gx. So if there are different fluids, like this is fluid number one, this is fluid number two, this is fluid number two, like you can consider the example like, and this is mercury, this is water, and this is one of the oil. Then we can find out pressure at any location. So pressure at this location is atmospheric pressure. In terms of gauge pressure, that is zero. Pressure at this location, let us consider these points. This is A, B, this is C, and this is D. So pressure at point A, in terms of gauge pressure, it is zero. Pressure at point B is rho G H1. This is density of oil. Then pressure at point C is rho of water into G into H2 plus pressure at point B. Then pressure at point D we can write as rho of Hg into G into H3 plus pressure at point C. Remember, all these pressures are written in terms of gauge pressure. Likewise, you can find out pressure at any point in a static fluid. So based on this also, I have created two videos based on Pascal law and hydrostatic law. Please watch that videos so you will get better understanding of this Pascal law and hydrostatic law. Then manometers. So we know that manometers are devices used to measure the pressure. There are different types of manometers, like simple manometers are there, differential manometers are there. Simple manometers will measure the pressure at a point, while the differential manometers will measure the pressure difference between 2 points. So simple manometers has type like piezometer, YouTube manometer, and single column manometer, that is also known as micromanometer. And differential manometers has types like YouTube differential manometer and inverted YouTube differential manometer. So this is piezometer. Piezometer is just a simple vertical tube having diameter more than 8 mm, just to avoid the capillarity effect. And by using the height in that piezometer tube, we can measure the pressure. So suppose this is the cross section area of the pipe and we have attached piezometer to that pipe. So by measuring this height h, likewise we can likewise YouTube manometer also there. In case of YouTube manometer, manometric fluid is there, that is indicated by this blue color. So by measuring these heights h1 and h2, we can find out the pressure at point A. Suppose this is point A. So we can balance the pressures at a line such that on either side of that line, there is only one liquid. So we can draw the line at this section. So we can see that on bottom side of this line there is only one fluid. Okay, so this is my datum line that indicates that the pressure at this point and pressure at this point is same. Now we can find out pressure at this point by using the hydrostatic law. So that we can say that it is Pa plus, let us consider density of fluid is rho 1 and density of this fluid is rho L. So Pa plus rho 1 G H1 This is the pressure in the left limb up to this point, and that is also equal to rho m g h2. This is the pressure in the right limb up to this point. So by using this, we can find out pressure at point A or pressure inside the pipe. Likewise, single column manometer is also there. In case of single column manometer, by measuring this height S2 only, we can find out the pressure. Then YouTube differential manometer is there, that is used to measure the pressure difference between the two different pipes or in the same pipe at two different sections. In order to measure this pressure difference, we can use the YouTube differential manometer. So again, the thing is same, like we have to just draw one datum line and just we have to balance the pressures at the datum line. So pressure at this point and pressure at this point is same. So by using that, we can find out the pressure difference between these 2 points. Likewise, inverted YouTube manometer is also there. So in this case also, we can find out the pressure difference between these two pipes, that is PA and PB. Okay, so question may be asked like you have to find out the pressure difference, or if the pressure difference is given and you have to find out any height. Okay, so that kind of questions may be there in the exam. So try to solve such kind of numericals. Then the manometers may be like this. Okay, so in this case, by using earlier method, it is little bit difficult to find out the pressure difference. So in this case, we have to use another method, like we can move from one point towards the another point. Okay, and by using that, we'll find out the pressure inside this pipe. Okay, or pressure difference. So like in this case, first we have to draw the datum line. We have to draw the datum line such that on either side of datum line, there should be only one fluid. So let us draw a datum line for this YouTube manometer. We have to draw the datum line here only. That indicates pressure at this point and pressure at this point is same. Likewise, for this inverted YouTube manometer, we can draw the datum line at this location. So pressure at this point and pressure at this point is same. Likewise, for this third YouTube, we can draw the datum line here. So pressure at this point and pressure at this point is same. Okay, I'll use another color. So we can go from this point up to the pipe. Okay, so at this point pressure is 370 kilopascal, that is given. So this we can write as 370 into 10 raised to 3. Then this, from this point we are moving downward direction, but we can see this is air, and air does not have that much density. We can see density of water is 1000 while density of air is 1.2. So this whatever the pressure generated because of this height of air, that we can neglect. You can find out that also, but that you can neglect. Then whatever the pressure at this point, just we have moved in downward direction. Whatever the pressure at this point, same pressure is there at this point. Okay, now from this point we are moving in upward direction. So as we are moving down upward direction, pressure goes on reducing. So that's why we have to put minus sign. Okay, then density of this fluid, that is water, so that we can write as 1000 into G, that is 9.81, into height is 45 centimeter, so that is nothing but 0.45 meter. So that is pressure up to this point. Whatever the pressure we have written, that is pressure up to this point. Now from this point, whatever the pressure at this point, same pressure is there at this point. Okay, now again from this point we are moving downward direction, and this fluid, orange color fluid, is oil of specific gravity 0.79. Okay, since we are moving downward direction, so that's why we have to add. So we have to use the plus sign. Then we are moving downward direction, so we can find out the pressure, that is 790, that is the density of oil, into 9.81, into height is 50 centimeter, that is 0.5 meter. This is the pressure up to this point. Okay, so whatever the pressure at this point, same pressure is there at this point. And from this point we are moving upward direction, so minus sign will be there. So minus, then whatever this fluid is there, it has a density 13,600, since it is the mercury, so 13,600. into 9.81 into height is 10 centimeter, that is 0.1. That is the pressure up to this point. Again, from this point we are moving upward direction. So again negative sign. And the density of this purple color fluid is 700. So 700 into 9.81 into height is 22 centimeter, that is 0.22. That is pressure inside this pipe. So by doing this calculation, we can find out what is the pressure inside this pipe. Then let's move to the hydrostatic force. So hydrostatic force, it is force because of the pressure. So in some books, they are writing this hydrostatic force as total pressure or total pressure force. Okay. So whenever we are talking about the force, we need the three things, that is magnitude, direction, and point of application. So hydrostatic force, this magnitude we can find out as pressure at a center of gravity, okay, into area of that plane surface. So whatever the pressure at center of gravity of that plane surface into area of the plane surface, by using that we can find out magnitude of the hydrostatic force. Then direction is always normal to the surface because this force, hydrostatic force, is because of the pressure. And point of application, that is also known as center of pressure. Now in different cases we'll try to find out this hydrostatic force and center of pressure. Four different cases are there, that is horizontal plane surface, vertical plane surface, inclined plane surface, and curved surface. So in these four different cases we can find out hydrostatic force and center of pressure. So just I'm writing final formula. I'm not doing any derivation here. So for the horizontal plane surface, we can find out this force as rho g a into x bar, where x bar is uh, distance of cg of the plane surface from free surface of the liquid. And A is area of that plane surface. Rho is density. So by using that, we can find out this hydrostatic force. So in this horizontal plane surface, let us consider this is your horizontal plane surface and this is your height h, and that is also equal to x bar. This is also equal to the x bar because CG of this plane surface will be somewhere here. So x bar is a vertical distance from the free surface of the liquid up to the CG. So by using this formula, we can find out the hydrostatic force, that is rho g a into x bar. Always use SI units so that finally we can write the unit of this hydrostatic force is Newton. Then h bar is center of pressure. H bar is center of pressure. In this case only, the horizontal, in case of horizontal plane surface, this h bar, that is center of pressure, is equal to the x bar. Okay, this is in case of horizontal plane surface only. Now, in case of vertical plane surface, again the formula remains same. That is rho g a into x bar. The formula remains same, but the center of pressure will change. So, in case of vertical plane surface, center of pressure is x bar plus Ig upon Ax bar. So, remember, so suppose this is your vertical plane surface and this is the location of C surface. So, this distance is nothing but x bar. This distance is nothing but x bar. So remember always h bar is more than x bar in case of vertical plane surface or in any other cases apart from horizontal plane surface. Except horizontal plane surface, h bar is always greater than x bar. So if it is a competitive exam and if you want to find out the h bar, then please check what is the distance of x bar. If the option, any option whose value is more than this x bar, then you can directly take that option. So this force we can find out by using this formula rho g a into x bar, and h bar we can find out as x bar plus Ig. Now Ig means moment of inertia of this plane surface. So if I draw the another view of this plane surface, then this is my plane surface. Let us consider it is rectangular. So Ig is this Ig. So moment of inertia with respect to axis passing through the center of gravity. We have to find out that, and by using that only we can get this h bar. So that is Ig divided by A into x bar. So by using this, we can find out the center of pressure. Likewise, in case of inclined plane surface, again the formula is remains same. That is rho g A into x bar. Okay, in case of inclined plane surface. But remember, in case of inclined plane surface, let us consider this is location of CG. Okay. Then if I project that CG, so in case of inclined plane surface, this is your CG, and this vertical distance is nothing but x bar. Okay. So by using this x bar, whatever the area, like this area, and specific weight of the fluid, we can find out the hydrostatic force. So we can see this hydrostatic force is independent on this angle theta. Whatever the angle theta is there, whatever this for this inclined plane surface, there is always some angle theta with respect to horizontal, and this hydrostatic force is independent on this angle theta. Okay, but center of pressure it depends on this angle theta. Okay, so center of pressure we can find out as x bar plus Ig sine square theta divided by ax square. Okay, it is similar to that of vertical plane surface, only this thing is extra thing. Okay, so you can remember this formula, and for the vertical plane surface we know that this angle theta will be 90 degree. So sine theta is 1, sine 90 is 1. Okay, so by using this you can reduce that formula. So you can remember these two formulas only. So once you remember these two formulas, you don't have to remember any other formulas. Okay, so likewise in case of curved surface, okay, there is some mistake. So this is not vertical plane surface, it is a curved surface. So in case of curved surface, instead of calculating directly this resultant force, we are calculating components, horizontal component and vertical component. So horizontal component, it is based on vertical projection of this curved surface. So if this curved surface is AB, then we can draw the vertical projection of this curved surface. So here I am drawing the vertical projection of this curved surface. Okay, so this is my projected area. This is my projected area, and by referring this image only, I have to find out horizontal force or horizontal component of this hydrostatic force. That is rho g into AP. AP means this projected area, whatever this distance is there. Let us consider it is A. This height is B. So AP we can find out as A into B. X bar of projected area is projected area का whatever the X bar is there from the free surface of the liquid, that you have to consider. So by using this we can find out this horizontal force, and vertical force is very easy. We have to find out the weight of the fluid supported by the curved surface. So whatever this curved surface is there, or which whatever the weight is there, weight of this fluid element is there, that you have to consider, and by using that only you have to find out this vertical component of hydrostatic force. Okay, so weight we can write as rho g into volume. Okay, so rho g is specific weight of this fluid and volume over this curved surface. So curved surface के ऊपर जो भी volume है fluid का, that you have to consider, that you have to find out, and that value you have to put here. Just by putting that value you will get the vertical component of hydrostatic force. Once you get the horizontal component and vertical component, you can find out the resultant force. So resultant force is square root horizontal component square, horizontal force square plus vertical force square. So by using that you will get the resultant force. Likewise, you can find out its location also. So this is the location for horizontal force, and this is the location for vertical force. Let's try to solve some new sample numericals. Okay. So there is one gate in this numerical. You can see there is one gate AB. Okay. So this is your gate. You can see AB. And this is one pipe, you can see, and the fluid is located here. So this is your fluid, and you can see this is horizontal plane surface, and the fluid pressure will act in this direction. This direction the fluid pressure will act, or in other words we can say that in this direction the hydrostatic force will act, and we want to find out this force. Okay, so this force is, you know the formula, it is rho g a into x bar. Okay, so just put the values. So you can see in the numerical it is water, so density is 1000, so it is 1000 into g is 9.81 into area of this plane surface. So here it is 3 meter is written. Now second dimension, that for that you have to read the numerical. So it is given 4 meter wide. Okay, so this plane surface, this gate is just like this. Okay, so this dimension is 4 and this dimension is 3. So area you can find out, it is 4 into 3 into x bar, whatever the location of centroid from the free surface of the liquid. So centroid of this plane surface is located somewhere here. Now is distance from the free surface. Free surface is this one. So this is your x bar. In case of horizontal plane surface, this is also equal to h bar, right? So x bar is 5 meter in this case. So by using this, you can find out this hydrostatic force. So its value is somewhere around 588.6 kilonewton. Then actually in the question, you have to find out how much force is acted on this point E. Okay, how much force is acted on this point A. Now for that, we have to consider the moment about the hinge. Since it is a hinge, so moment about the hinge is equal to 0. Okay, so we can write it like F at point A into 3, that is equal to this hydrostatic force F, and that will act at the centroid. So it is at a distance 1.5 meter from the hinge. Okay, so this F value we know, that value we can put here. Ultimately we can find out the force acting at point A, and that is approximately 294 kilonewton. Then this is numerical based on vertical plane surface. Again, the numerical is 3 meter. This is one gate. You can see this is one gate, and its height is 3 meter, and this is the hinge, and it is 6 meter wide. So if I draw the another view that you have to draw in case of vertical plane surface, so the view will be like this. So this plane surface, vertical plane surface will be like this. So this distance is 6 meter, and this height is 3 meter. Okay, and you have to find out the hydrostatic force exerted on the gate, and the liquid is 5 meter height from the bottom, and you have to also find out the location of center of pressure center, that is center of pressure, that you have to find out. Okay, so the formula remains same. So F is equal to rho g a into x bar. Since it is the water, so rho is 1000 into g is 9.81, area is 6 into 3, and distance of x bar. Now for that you need the centroid. So we know that for the rectangular plate, the centroid will be somewhere here, and this distance will be 1.5. Remember, x bar is the distance from the free surface of the liquid. Okay, so this distance is 1.5. This distance is 1.5, plus we have to add this 2. So our total x bar is this. This x bar is a 2 plus 1.5. So in our case, x bar is 2 plus 1.5, that is 3.5 meter. Okay, so that value I'm putting here, 3.5. So you can find out this hydrostatic force acting on this gate, this magnitude you can find out. Then center of pressure you can find out as x bar plus Ig upon Ax bar. Okay, x bar we have calculated, it is 3.5, plus Ig you can find out as BD cube by 12, since it is a rectangle. Always you have to see this projected area. So B is 6 and D is 3. So BD cube divided by 12, that is Ig, upon area is 6 into 3, and x bar is 3.5. So once you do this calculation, you will get the h bar, that is center of pressure. The question may be asked like how much force is exerted at point B. This can be the question, extended question. So in that case, you have to consider the moment about the hinge, that is equal to 0. So FB into 3, that is equal to whatever your hydrostatic force into distance is. Let us consider your hydrostatic force is acting at this point. So this will be the height h bar, but we want distance up to the hinge only. So that will be h bar minus 2 meter. Okay, so by using this, you can find out what is the force exerted at point B. Okay, at any moment of time, if you feel there is some doubt, you can put your doubt in the chat box. I'm happy to answer your doubt. Then this is inclined plane surface, and we want to find out what is the hydrostatic force in this inclined plane surface. You can see here it is written, it is 2 meter wide gate. That means perpendicular to this paper, the dimension is 2 meter. Okay, that means we can draw the another view like this. So this is my other view. And this distance is 2 meter. This distance is 2 meter. You can find out this dimension, since it is this one is 4, this one is 3, that means this one will be 5. Okay, that you can find out by using Pythagoras. Okay, so this distance is 5. So by using this, you can find out the area is 5 into 2. So area of this plate, we can say it is 5 into 2, so it is 10 meters square. Okay, then we need the x bar. So CG is somewhere here. Okay, so this distance will be 2.5 meter. So you can project this CG here. So this is your CG. Remember always x bar is a vertical distance from the free surface of the liquid. So this is your x bar. Anyhow, you have to find out this x bar. But after calculating this x bar, you can able to find out the force, that is rho G A into x bar. Okay, area is this one, x bar. Now in order to find out the x bar, you may need the angle also. So in some numericals the angle is provided, but here the angle is not provided, but distances are given. So you can find out like what is tan theta. So let us consider this angle is theta. So tan theta is 4 divided by 3. So theta will be tan inverse of 4 divided by 3. Okay, so by using this and by using this angle, sorry, by using this triangle, you can find out this vertical distance. Let us consider this vertical distance is x1. Once you got the angle, you are able to find out the vertical distance, because this distance is 2.5 meter, and angle you know, so you can find out the x1. Once you got the x1, you can easily find out the x bar, and by using that x bar, you are able to find out the hydrostatic force. Okay, now in order to find out center of pressure, it is x bar plus Ig sine square theta divided by ax bar. Okay, x bar you already calculated, so that value you can put here. Then Ig you can find out as BD cube divided by 12, since it is a rectangular. So BD cube divided by 12. By using that, you can find out Ig. Angle you already calculated, so just put this value, you will get the h bar. Okay. Then likewise, for the hydrostatic force in case of curved surface, normally in case of curved surface, you just have to find out the force. Okay, the numericals are like you just have to find out the force. You don't have to find out the location in many cases, because If you find out the force and if you want to find out the location also, the numerical will be lengthy and the higher weightage should be provided. It's not that such kind of numericals will not be there. Such kind of numericals may be there, but the weightage will be high. Okay. So you can find out in case of curved surface, you have to find out resultant force. So in order to find out resultant force, you have to find out horizontal force and vertical component of the force. So for the horizontal force, you have to use the projected area. So rho g projected area and x bar of projected area. So in this case, see carefully, this is your projected area. So for this projected area, height is 2 meter. Why 2 meter? Because this distance is 2 meter and this is one fourth part of the circle. So this distance is also 2 meter. Okay. So this is 2 meter and this distance it is given width of AB is 1 meter. So this distance is 1 meter. So your projected area is 2 into 1, that is 2 meter square. Okay. And x bar of projected area, that is, suppose this is the centroid CG, or simply we can write G. Then this distance will be 1 meter. And you can see this height up to this point, it is 4 meter. So 4 plus 1, that is 5 meter. So x bar is 5 meter. Always you have to consider in case of curved surface, in order to find out horizontal force, you have to draw this projected area and just you have to consider this projected area just like a vertical plane surface immersed in a fluid. Okay. And by using that, you have to find out this horizontal component. Okay. So you can put the values. Let us consider this is water. So this value is 9810 into area is 2 and x bar of projected area is 5. So by using this, you can find out horizontal component. Then vertical component is rho g, that is equal to the weight of the fluid supported by this curved surface. So that is specific weight into volume. Okay. So anyhow, you have to find out the volume of this fluid above this curved surface. So whatever this volume is there, that you have to find out. So in other words, we can say that volume is this front area into perpendicular distance. So this front area, complete area into perpendicular distance. So front area you can find out as this area plus this area. Okay. So rho g is 9810 into volume I can write as A1. Let us consider this is A1, this area is A1 and this area is A2. So it is A1 plus A2 into thickness. Thickness perpendicular to this plane is 1 meter. So that you can consider. So this is nothing but volume. So it is 9810. A1 we can find out as 4 into 2. So A1 is 4 into 2 plus A2. A2 is 1/4 part of the circle. So it is pi r square divided by 4. So pi into 2 square divided by 4. So this one is A1, this one is A2 into 1. So by using this, you can find out what is this vertical force. Okay. And once you got this horizontal component, vertical component, it is very easy to find out resultant force. Okay. Similarly, in the question, if it is asked to find out the location, you have to find out h bar of this horizontal and h bar of vertical. Okay. Then last thing from this first unit is Archimedes principle and buoyancy. So Archimedes principle is said that the upward buoyant force that is exerted on the body whenever body is immersed partially or fully inside the fluid, it is equal to the weight of the fluid that is displaced by the body. Okay. And whenever we are talking about the force, we need the three things. One is its magnitude, then second is direction, and third is point of application. So magnitude of this magnitude of this buoyancy force we can find out as, so this buoyancy force is specific weight of the fluid into volume of the fluid displaced by the body. Displaced by body. Again, remember this buoyancy force is resultant of hydrostatic force. Okay, so by using this, you are able to find out magnitude of buoyancy force. Direction of this buoyancy force is always in vertically upward direction. Buoyancy force always act in vertically upward direction. And point of location, that is also known as center of buoyancy. Okay. So there are two bodies you can see on screen. It is partially immersed body and fully immersed body. So for the fully immersed body, volume of fluid displaced by body, that is equal to the volume of the body. But in case of partially immersed body or floating bodies, the volume is this volume only. You can see. Oh, okay, just try to draw isometric view. So whatever the volume displaced by the body, that volume you have to consider in order to find out buoyancy force. Center of buoyancy, you can see center of buoyancy in these two cases will be different. So center of buoyancy, where the buoyancy force will act, or we can say that in other words, center of buoyancy, center of gravity of displaced volume. So whatever the volume is displaced by this body, uh, whatever center of gravity of that displaced volume, that is nothing but center of buoyancy. Okay, so in case of floating body, this is the center of buoyancy. In case of fully immersed body, we can say that center of gravity and center of buoyancy will coincide. Okay, then buoyancy force in case of floating bodies. So in case of floating bodies, since the body it is in stable equilibrium, so we can write summation of Fy0. So that means a buoyancy force that will act in vertical upward direction, that is equal to the weight of the body. But remember, this is in case of floating bodies only. That is in case of submerged bodies only. In case of a fully immersed body, we cannot write like this. So in case of fully immersed body, summation of Fy it is equal to 0. That is buoyancy force plus normal reaction, that is equal to the weight of the body. Okay. So we cannot say always that buoyancy force is equal to the weight of the body. Depends where if the body is floating body, then we can say that buoyancy force is equal to the weight of the body. Then different stability criteria are there. For the submerged body, if the buoyancy force is above, if the buoyancy point is above center of gravity, then the body it is in stable equilibrium. Stable equilibrium means if I apply small force to this body, after some time the body regain its original position. Like you can take the example of parachute. Parachute is fully immersed in the air. Okay. And in case of parachute, center of buoyancy is somewhere here, center of gravity is somewhere here. Now, if I apply small force to this parachute, after some time, the body will regain its original position. The body will not fall. Okay. That means this is in stable equilibrium. This is in stable equilibrium. So for the stable equilibrium, the buoyancy point should be above the center of gravity. Center of buoyancy should be above center of gravity. In case of unstable equilibrium, the center of gravity will be above center of buoyancy. The body will be in unstable equilibrium. In case of neutral equilibrium, center of gravity and center of buoyancy will coincide. This is in case of submerged bodies. In case of floating bodies, apart from these 2 points, center of buoyancy and center of gravity, one more point is there, that is meta center. And relative position of this meta center and center of gravity will tell us whether the body it is in stable equilibrium or whether it is in unstable equilibrium. So for the stable equilibrium, if the point M is above G, then it is in stable equilibrium. Okay. If the M is below G, then it is unstable equilibrium. If M and G coincides, then it is in neutral equilibrium. Okay. Meta center we can define as a point about which the floating body oscillates. Okay. So we can see the same thing. GM indicates metacentric height. Metacentric height is distance between center of gravity and metacenter point. Okay. If this distance is positive, then also we can say that the body it is in stable equilibrium. If this GM is negative, then it is in unstable equilibrium. If this GM is 0, then it is in neutral equilibrium. Okay. So finally, we can say like this. These are equilibrium